This slide shows us the graphs of a time domain NMR data set and its spectrum obtained by Fourier transformation, which in this case transforms time domain data into a frequency domain spectrum. The example perfectly tells us that M0 can contain a lot of NMR frequencies, which can be nicely presented by different peaks in a spectrum. It is just a preface to introduce Fourier transformation, which is a method of essential importance in all modern spectroscopy. And hence, understand how it works is important. What is Fourier transform in NMR? Mathematically, it is a transformation that converts a time domain function, presented here as a lowercase ft, into a frequency domain function, presented here as an uppercase f omega, where t and omega are variables. In mathematical symbols, it says that the Fourier transform of a function ft in t domain results in a function in omega domain, denoted here as uppercase f omega, and defined by an indefinite integration of lowercase ft times the core of the transformation, i.e. e to the power of minus I omega t, from minus infinity to positive infinity. Here, omega is a variable induced by Fourier transform. Keep an eye on how the uppercase is used here to represent a function transformed, which is a spectrum in NMR. In our case, the lowercase ft is M0 times the spinning factor st times the waning factor wt. And for simplicity and clarity, we will consider an ft that contains only one single frequency and omit the amplitude M0 in the following context, because it is simply a constant in the formula. There is another important theorem regarding the Fourier transformation for the multiplication of two functions, which says that the Fourier transform of xt times wt in t domain is a function in omega domain. It is equal to the convolution of the Fourier transform of them, denoted here as capital S omega and capital W omega, where the asterisk is a symbol for convolution, and the result is simply the capital W with the variable changed from omega to bracket omega minus omega j, i.e. the Fourier transform of Wt centered at omega j. Question: where does the omega j come from? And why the result is like that? The answers: the omega j comes from St, and the multiplication of St with the core of Ft of Fourier transform effectively merges them into one, so that the core changed from E to the power of minus I omega t to e to the power of minus I multiplied by bracket omega minus omega j bracket times t, thereby simplifying the integration to contain only lowercase wt. And the Fourier transform of wt, which contains only a, is simply bracket a minus I omega bracket divided by bracket a squared plus omega squared. Now, the final step we need to do is to replace the omega in the expression with bracket omega minus omega j, which is due to the change of the core. Let's move to the next slide to see how the result look like. You may be a bit surprised to know that the Fourier transform of an NMR signal actually always results in data for two peaks, one from the real part, as shown on the left, and the other one from the imaginary part, as shown on the right. One is absorptive, and one is dispersive. In fact, we only need one of them, as they are correlated. We can produce the other one simply by a phase shift of 90 degrees. You can try to deliberately make a spectrum 90 degrees out of phase with Mastranova. Every peak then becomes dispersive. You see how the real and imaginary part of the peaks are formulated separately, where omega in the previous slide has been changed to omega minus omega j. By now, you should understand why we have been using omega j in our teaching, simply because omega j is a constant. And we want to make it look different from the variable induced by Fourier transform. Remember, we gave a formula for the calculation of T2 before. It is actually derived from the W real presented here. We see that at the center of the peak, where omega equals omega j, W real is equal to 1 over A, because omega minus omega j equals 0. To simplify the problem further, let omega j be naught, i.e., we consider a case where the peak is centered at the origin of the frame. At the half height of the peak, W real equals to a half of 1 over A. Substituting this value of W real into the equation, we then get omega squared equals A squared. And hence omega must be plus minus A, where the peak height is a half. I.e., we have two omegas. Omega 1 equals A, and omega 2 equals minus A. What is A? It is 1 over T2. What's the peak width? It is simply omega 1 minus omega 2, i.e. 2A. Therefore, T2 equals 1 divided by bracket 2 pi b, because the width of 2b is measured in hertz. So far, we have only talked about semi-classic theory of NMR. We haven't talked about spin-spin coupling because it can only be precisely explained by quantum mechanics. This slide, as you can see, contains a lot of wordings. And there are only conceptual statements, which you might have learned before. They are presented here just to introduce the contents of the next few slides, which are related to spin-spin coupling. To save the lecturing time for more difficult contents, I'll let you read through them in your spare time. Now, we want to talk about quantum mechanics formalism of NMR. The starting point is the Schrödinger equation. There have been a lot of complicated applications using the equation to describe quantum phenomena. And it's impossible to learn the details in a few lectures or even in a few months. But today we are going to learn from something we are familiar with so that we can quickly and easily grab the idea about how it is applied to NMR. The first thing to look at is the equation, which is shown on the slide. Before we read it, there are a number of concepts that we need to go through. First is about the symbols in the equation, where the psi t embraced by a vertical line and an angle bracket is called a ket in quantum mechanics. It is actually a column vector that contains components that represent the energy state of a spin system. In other words, every component of the vector represents one energy state. For example, if we have a spin system that contains only two spin half nuclei that are coupled to each other, there will be four energy states because we will get two doublets in an NMR spectrum, won't we? And two doublets indicate four NMR frequencies, i.e., we have four spin populations. Each of them are different in their NMR frequencies. I often feel a bit lucky and glad that we all know this basic concept of NMR. Next is about the curly HT. It is a matrix called total energy Hamiltonian that is built with the spin operators of the coupled system. For Chem 374, we don't need to worry about exactly how they are built. You can see my chapter 2 if you really like to know. And finally, the I is an imaginary unit due to the wave-like nature of the spin system. The discovery of Schrödinger equation is a milestone in the development of quantum mechanics. Erwin Schrödinger postulated the K equation in 1925 and published it in 1926. He was rewarded the Nobel Prize in Physics in 1933 for the discovery of new productive form of atomic theory. How Schrödinger discovered the wonderful equation was a mystery. But I'm sure you can at least have some understanding about this if you follow my statements below. Let's have a look at the similarity between the Schrödinger equation and the result of the derivative of y on the right, where y equals e to the power of minus I omega t. What is y? Sound familiar? It is the st, the spinning factor that we have learned before. What is the derivative of it with respect to t? It is minus I omega y. Have a look at this. If we multiply both sides of the equation by the imaginary unit I, it gives us an ordinary differential equation that is highly similar to the Schrödinger equation on the left, where when applied to a coupled system, y becomes the vector ket psi t, and omega becomes the total Hamiltonian ht. Apparently, the Schrödinger equation must also relate to something spinning. That is why it is also called Schrödinger wave equation. In addition, we also learned that Schrödinger equation has nothing to do with the decaying factor, which is perhaps another area for us to work with to get another Nobel Prize. How to get the solutions to the Schrödinger equation? Here it says that the solution to the equation is related to an eigenvalue problem, where the word eigen is a German word, which means characteristic or peculiar. What is an eigenvalue problem? What is an eigenvalue problem? In algebra, it is defined as follows. Given an n by n matrix A, a traditional eigenvalue problem involves in finding all or some of the non-zero n-element vectors vi's and corresponding scalars lambda i's that satisfy the equation A vi equals lambda I vi, where the lambda I is called an eigenvalue of the matrix A, corresponding to the eigenvector vi. Here, A is considered to be an operator that transforms vi into another vector. And in this case, the eigenvector vi is transformed into a vector that is parallel to AVI, with its length also being changed from 1 to lambda I. Now, have a close look at the eigenvalue problem in quantum mechanics. Here the operator is the Hamiltonian, and the eigenvector is the kth component of the ket psi t in the Schrödinger equation. In other words, the kth component in psi t is also a ket Moreover, the problem has been changed into a number of eigenvalue problems, and we can deal with individual components of psi-t in this Schrödinger equation one by one. Here, psi-kt is the kth eigenket, a characteristic vector, for the kth energy state. And Ek is the kth energy value, i.e., the characteristic value that represents the energy level of the spins in the kth energy state. Finally, everything is linked to the knowledge we have learned before. An eigenket represents an eigenstate, and an eigenvalue represents an energy level. How does a Hamiltonian look like? On the screen is the Hamiltonian of a system of two spin-half nuclei that are coupled with a coupling constant, J. In the Hamiltonian, omega naught is the average value of the Lambda frequencies of the two spins, and delta is the difference between the two frequencies. The metric is formed by mathematical derivation with the frequencies, the coupling constant J, and the system's base operators, as shown in my chapter 2. With this Hamiltonian, 4 eigenvalues and 4 eigenvectors are found by solving the eigenvalue problem mentioned in the last slide. Have a look at what the values of the E's are, where the R is the hypotenuse of a right triangle, as shown on the right, which can be worked out by delta and J using Pythagorean theorem. Now we got the calculated energy levels of 4 energy states due to coupling, which come from the solution to the Schrödinger equation. What about the eigenvectors? As expected, we got 4 of them, each of which represents a spin population. Apparently, the first one is for the population in which both the coupled nuclei are spin up. And similarly, the fourth one is the population in which both the coupled nuclei are spin down. How to understand the second one and the third one? It means that in the population, there's a certain probability of nucleus 1 to be spinned up while nucleus 2 is spinned down. And there is also a probability for nucleus 1 to be spinned down while nucleus 2 is spinned up. So we got 2 probabilities here. Be aware that the probability in quantum mechanics is the square of the parameters in the above equations, i.e., either cosine square phi or sine square phi for situation 2 and 3. And hence, in each of the populations, the summation of the probabilities is 100% because cosine square phi plus sine square phi equals 1. Where phi is defined also by a right triangle, as shown. How about the resonant frequencies? As expected, we also have 4 of them, as shown on the right. They are calculated by delta E's, i.e. Ej minus Ei, which gives us the resonant frequencies omega Ji, where the Ej's are shown in the last slide. I'll let you do the derivation as an exercise in your spare time. If you plot them on an axis, there will be 4 lines, as shown on the next slide. These are the peak patterns we can obtain with different ratios of J to R. In the first 2 cases, we got 2 doublets. In the third case, we got 2 singlets, because J equals naught. And for the fourth one, we got only a singlet because their NMR frequencies are the same. In the first case, the doublets are skewed. This phenomenon can be observed when J over R is significant. When J over R is less significant, no skewness will be observed. Quantum mechanics also allows us to work out the intensities of the lines. The formulae obtained are shown on the left. As you can see, the intensities are significantly affected with different values of the J-R ratios. Here is a good example to show the coupling patterns of 2 spin-half nuclei. We got a molecule with 3 CH2 groups that result in 6 doublets in the spectrum, as indicated by the dotted boxes therein. The NMR frequencies of the 1H's in each of the CH2 groups are slightly different from each other, which allows us to observe the skewness of the doublet. The 2 doublets at around 4.5 ppm are skewed significantly, whereas the 2 doublets on the flanks of box 3 are just slightly skewed because they are further apart. This concludes my lecture 4. So far, we have learned the fundamental theory of NMR. We described them with semi-classical approach first, and then the quantum mechanics approach. As you can see, I have tried to speak slowly and clearly so that you can follow me and absorb the contents relatively easily. Once again, I sincerely and strongly recommend you to open your mind and learn. Tell yourself that you can learn and you will. The rest of the lectures are practical and easy to be understood. Therefore, I will talk much faster.